evening, Dr. Good evening, colleagues. We'll be presenting today our second presentation with the senior thesis one, the Alamillo bridge. Let me introduce my colleagues, Reem, Amira, Shadi, and Mustafa. First, we give us a brief introduction for our scope of work for the first presentation, and then we talk about the load applied in our analysis, the proposed material, the deck construction method, aerodynamics modeling, and structure optimization, and the piling parametric cell. Our scope of work is to design the superstructure of the bridge, which are the cables and piling, and the substructure of the bridge, which is the foundation, and the different piece of load. Besides the load that we have of the bridge, we have life load. First, there is a vehicular load specified in the H2 as a truck load or a tandem load. We take the truck load because it's heavy, and we take the HL93 truck with the given configuration, and the transverse distribution in the figure. The lane width is 3.6 meters, and the load is distributed on 3 meters wide all around the bridge. And the pedestrian load will be in the middle of the bridge between the middle racks, 3.16 meters per meter square. And above the superimposed load, there is a weighing surface, which is the asphaltic area. It is 0.95 meters per meter square, and the curves are on both sides of the bridge. It is 120 centimeter wide and 30 centimeter height, and the railings are two tube curves mounted. It is 85 centimeters high above the curves. The proposed materials are noble-weight concrete, sand-lightweight concrete, and lightweight concrete. The noble-weight concrete has a very high compressive strength with high density, and lightweight concrete has a very low compressive strength with low density. So we compromise by taking the sand-lightweight concrete because it has good compressive strength, which is 47 megapascal and 1.89 density. The cables will be high strength steel that has ultimate strength 1,260 megapascal and the yielding 1,760 megapascal. The cross section, the proposed cross section from the first presentation was a hexagonal steel box with long steel cantilevers, or a hexagonal concrete box with long steel cantilevers, or a multi-cellular concrete box section. We found that the multi-cellular concrete box section is better from the other two alternatives because it has higher torsional stiffness and higher bending stiffness and lower amplitudinal vibrations. After doing some basic assumptions, the proposed cross-section is 42 meters wide, 3 meters high, and the middle ones we meet in the middle of the bridge because the cables will be attached to the corbel, attached to the webs. And the rest of the space will be very wide to do it hollow, and it will be very heavy to do it full of concrete. And about the construction method, it will be segmental. We pour the first segment from the deck and the pylon, and attach the first cable and apply tension to it, and then the second segment and the third until we finish the bridge. There is two ways to construct the segmental method. Precast segments or cast in place. The precast segments during the construction, the handling moment will be as shown because it will be a cantilever. So the pre-stressing cable should be in the upper part of the deck. And after the construction, the landing moment will be like the cable because it will act as a simple supported beam. So the pre-stressing cable profile should be as follows. So we have to do two systems of cables, which will be very expensive and innovative. So we go for the cast in place by using shoring in order to coffer dam by changing the direction of the water to another branch, or build the the bridge on the side of the river and rotate it from the river, or by using a watch. So now I will leave you with the aerodynamics.
As for the aerodynamics, the prime concern of the bridge design is the wind load. So our objective, because if the wind velocity exceeds the critical velocity for flutter that the bridge can withstand, this will lead to the failure of flutter, whereby Tacoma's bridge in Washington is a classical example of this failure. So it's important to conduct an aerodynamics analysis for the bridge. Our objective of the study is to select an aerodynamic shape for the deck to study the dynamic effect of the wind on the deck by maximizing the downward force on the deck. The methodology is a two-dimensional analysis of the wind flow on the deck. Actually, the software used Gambit and Fluent. The model geometry and mesh were created by Gambit, and the analysis were done by Fluent. The Gambit, the model geometry is drawn around it, and a control volume is drawn around it, representing the wind tunnel. Then for the Fluent, it is only for the analysis. Then after drawing the control volume, we are representing a two-dimensional surface, representing the finite element analysis, then exporting the model to Fluent and running the model on the Fluent using the computational fluid dynamics, the CFD analysis. As for the Gambit, there is major concern for the grid generation and the grid type. The grid is the most vital part in the Gambit because the accuracy of the grid will help us to make sure that the results are accurate. And the grid type used here is the quadrilateral wave mesh. As for the Fluent, this CFD software solves the dynamic equation in an iterative manner, and it has the steady and unsteady. So we're actually using the steady because we're investigating the effect of the maximum angle at a constant time. The problem, we have the geometry of the problem. It is the cross-section of the deck, and the variable is the angle. We're using 8 different angles, ranging from 55 to 143 degrees. The boundary conditions which we will set on Gambit, the wind speed of 4.5 meters per second, and viscid flow of almost zero viscosity, and the pressure is set 1 atmospheric pressure, and the model run on a K epsilon flow. The procedures of the solution will draw and generate required sheet mesh, then setting out the boundary condition in Gambit, and exporting and running the model in Fluent, and finally plotting the results. Actually, after running the 8 angles, we got the angle 55 here in the shown figures. We have the pressure contour diagram. This is the pressure contour. It shows the pressure distribution on the deck in the section domain. We can see here that the pressure concentration is maximum at the nose of the bridge, at the front of the bridge, while here it's subjected to a negative pressure or suction. Actually, similar for the velocity contour, here it is the maximum at the nose of the bridge, at the front of the bridge, while at the wake it's a lower velocity. Finally, after running 8 different angles, we got that angle 55 gave us the maximum downward force, and its frequency is different from the natural frequency of the bridge, which ensures the stability and an unobstructed behavior. Thus, we have a safe and stable bridge regarding the aerodynamic response. Finally, we have to do a result validation to make sure that the variables we entered in the software is correct. So we did an air flow around the cylinder. It's an inviscid flow, and we matched our results with the results that came from the software. And we have it's correct and accurate because it's matched the exact model. And finally, I want to raise a point about the circular shape. It's the worst shape for the wind because of the wind cross vibration due to the layer separation. This is a point we're going to consider while designing our layers. And now the model.
As for the modelings, we have 3 main elements to be modeled in our bridge: the cables, the connections, and the deck. We'll start first with the cables. There is 3 techniques to model the cable: frame, tendon, or cable. As for the frame, they can be modeled as a frame that has a moment release in both ends to avoid moment transfer between the deck and the pipe. As for the tendon cables, they are almost the same. However, the tendon The tension in the forces do not increase when the load on the deck increases. However, the cable, the tension in the cables increases when the loads in the deck increase. So we decided to model our cables as a cable element, not as a frame or tank element. And for the connection modeling, there is two important connections to be modeled: is the pylon deck connection and the pylon cable connection. Since we model our pylon as a single frame element, so there is a dramatic difference between the cables and the pair of cables and the pylon, and between the deck and the pylon. So we had to make a rigid link member. Between the cables and the pylon, and between the deck and the pylon, to allow moment transfer and to simulate the reality. As for the deck modeling, there is three techniques: spine, village, and area. As for the spine, we modeled the whole cross section as a single frame element. It's easy to understand the global behavior. That in our bridge is a simple beam behavior. However, it has a very poor transverse behavior. And the second one is the grillage. It's closer to reality than the spine, and it has a better transverse behavior. For the third one and the last one is the area element, that we model each and every element in our deck as an area element. Though it's closer to reality than the grillage, however, it requires more computational time, almost triple or quadruple the time. And since the support is simulated as pin supports, it magnifies the negative moment and underestimate the positive moment. So we conclude that we will model our deck as a grillage. For our grillage, we have this cross section, and we divide our cross section into 6 I-beams. We make it this irregular shape in order to allow that is centroid to be coincides with the y-axis of the neutral axis of the whole cross section. And we make an Excel sheet to calculate the general properties that we will use in the SAP 2000. In our grillage in SAP 2000, we model each and every the same colors with the longitudinal members with the properties, and we set its weight modifier to be 1 to calculate the dead load. However, in the transverse members, we set its weight modifier to be 0 to avoid the double counting of the dead load. As for the transverse members, usually the mesh of the transverse member is span over 40 or span over 20. Usually this is for the short span bridges, but our bridge is a long span bridge. So after searching in similar bridges, we decided to make span over 200, and this make the space between the mesh is 2 meters. And there's the yellow one is the nominal members, and they don't contribute in our calculations. They are only used to link the longitudinal and transverse members together. And now I will do analysis methods.
Regarding our analysis methods, there is a p-delta force analysis. In that analysis, we apply a p-delta force or assign a p-delta force for each frame that's modeled as a cable, and then we run the SAP continuous an iterative process until it converges to the forces assigned in that analysis. The other type of analysis is the nonlinear analysis. It takes into consideration the geometric nonlinearity in the cable behavior. There are 2 types of analyses, sub-analyses under that umbrella. The target force analysis, in which it's quite the same like the p-delta force analysis. However, it did not yield good results because it has to converge to the certain number that we have inputted in the software. So we resorted to the p-delta analysis with large deformation. In that we take care that type of analysis takes care of the large deformations and the p-delta effect and the bridge behavior. We started with the initial dimensions of a top slab thickness of 25 centimeters, bottom slab thickness of 20 centimeters, width thickness of 60 centimeters, and cable areas of 35 centimeters squared for all cables. However, we changed that later. And then we started with the spine model. As you may know, we have 2 pairs of cables. So we modeled, at first we modeled each pair with 1 frame element and then we ran it. We got cable forces approximately equal to the segment weight that is carried by each pair. We got a mid-span dead load deflection of 2 meters and 54 centimeters. Then we moved to the grillage. We used cable elements. We used a cable to represent each cable instead of one frame to represent each pair. And we jacked the cables with half of the values we got from the first iteration. And then we got quite the same results of the previous one with that reflection. As you can see here, it's 1.73 meter because the cables were already jagged. Plus some losses of the forces. The forces increased in the cables because of the non-linear behavior. The mid-span dead load and live load deflection were 2 meters and 5 centimeters. Now these numbers are very big and they are not acceptable because basically the structure is not optimized. So we had to optimize it. We optimized the deck. We decreased the web thicknesses from 60 centimeters to 40 centimeters. And this reduced the deflection of the dead load by around 40 centimeters. So it's now 139 centimeters, and the dead load and live load deflection was 171 centimeters. And then we started increasing the tension in the cables, so we increased the stiffness of the cables and that reduced the deflection in the deck to reduce or almost eliminate the dead load deflection. And after tightening them, we reached a mid-span dead load deflection of 6 centimeters upward. It's a positive deflection, as you can see. I will show you later. Then we decided to apply a camber so that we take into account for the live load deflection. There are 3 types of camber. The first one is due to cable forces, by which we increase the tightness of the cables, or a pre-stressing system that applies the camber. However, this was expensive. And finally, the construction camber by building the bridge curved up a little bit so that when it deflects, it returns back straight. But usually the camber required is to account for the deflection due to the dead load and half of the live load. However, in our case, because we almost eliminated the dead load deflection by tightening the cables, we are required to make the camber to account for the half of the dead live load. As you can see here, that's a graph between shows the relationship between the deflection and the tightness of the cables. You can see here in the blue one, the upper one, there is an average of 10 meganewton force in each cable, and the deflection is the maximum deflection is 6 centimeters upwards. The other one was 8 meganewton. The deflection was negative 14 centimeters. In the other graph here, you can see the location of each cable in compliance with the station in the above curve. That's the little difference between the 2 forces of either around 10 meganewton or 8 meganewton. And as you can see here, the difference is a little. However, the deflection was completely safe. And now I will give you the pipe.
Now when we discuss the last element of the bridge, which is the pilot, we had to propose a new, it's not clear here, but we proposed a new cross-section for the pilot with a regular hexagonal shape in comparison to the irregular shape of the actual pilot with the cross-section. We made a quick comparison between the 2 different cross-sections. The actual cross-section has a high moment of inertia in order to resist the bending moment, which is the governing stress all along the pilot. But however, it's very difficult to design because of its complicated shape. It has a very lean aerodynamic characteristics. On the other hand, switching to the proposed cross-section, we have calculated its equivalent moment of inertia in order to be the same value as the actual pilot cross-sections, but it's easier to design, but unfortunately it has moderate aerodynamic characteristics. Going to the modeling of the pilot, we have 2 options: whether to use a subsection designer, which throws the section inputs the section into the sub, and it automatically calculates the different section properties. But it was very difficult to do such cross-section, so we had to modify it and model the pylon as a frame with a general section properties. In order to calculate the section properties, we use the software known as Shape Designer. This uses a matching technique in order to calculate all the necessary geometric properties such as moment of inertia, shear area, elastic modulus, and radius of gyration. And now we move to the part where we have to calculate the equivalent moment of inertia of the different pylon sections. We use the equation of a regular hexagonal shape in order to calculate the A, which is the side length of each section. Here we can see we formulated a table which divides the pylon into 16 different segments, each one with a different moment of inertia. And we use the rule seek or a solver add-in option in the cell in order to calculate the equivalent side length, which will eventually get the same value of the moment of inertia. So you see here, this is the target, which is the moment of inertia of the actual pylon, and this is the hexagonal or the calculated mean value. You see here at the very bottom, the first two segments has lower values than the actual ones. This was due to the fact that if we needed to calculate the actual moment of inertia directly, we would have to get a hexagonal shape with a side length of 8 square meters, which would contribute to a very large area, which was not permissible in our case. So we had to reduce the side length in order to make it read varying smoothly all along the pylon with small modifications.
Now, please, we would like to listen here, so please keep quiet.
So finally, this is the modified shape of the two segments, the first and the second segments, in order to increase our moment of inertia to the required values. Now we finally get to the last part of our presentation, which is the parametric study. The parametric study is an investigation of the effect of changing one variable over a system. We applied this concept on our bridge in order to investigate the effect of changing the inclination angle of the pylon. The aim of this study was to choose the optimum angle of inclination that would create minimum stresses all along our pylon, and this was the criteria for selection and comparison of the different angles, which are the moment, the shear, and the deflection. We create 7 different models. This is a schematic showing all the models laid on one drawing. We had the range of application plus or minus 9 degrees from the actual pylon angle, which was 58 degrees, and we increment the different angles by 3 degrees each one. After running a non-linear analysis of the dead load of the entire bridge, we concluded these results, which are the values for the criteria chosen earlier. And after plotting of these results, we conclude that we see here that these are the different criteria. See, this is the deflection, this is the moment, and the final one is the shear. We see here that there is a trend that is observed between the angle of beginning from the angle 49 till the angle 58, which is almost a maintained trend. However, at increasing the angle more than 58 degrees, you see that the trend is changing and the variation is very large. This is due to the fact that deflection is a double curvature deflection within the pylon, which induces more stresses. So finally, we reached the conclusion that the optimum angle of the inclination for the pylon is 57 degrees. It's only 1 degree different from the actual pylon. This is due to the fact that we chose the one with the minimum of zero deflection, and although it has a moment higher than the other value, like the 55 degrees, but this moment will be decreased due to the application of different variables. And finally, we got to our updated time schedule. You see here, this green part is where we achieved. This is the tasks that we achieved till now, and these are the one our future plans, inshallah. We see here that we still have some time for analysis, and we hopefully we are almost at the half of the back design. However, we still have the cables on the pylon and the design of the foundation. And finally, during the entire stage of the design, we will be producing design drawings. Thank you.
check the case that the wind speed is 10 miles per hour. Because that is critical wind in the area.
Actually, the wind is counted to be critical when exceeding 5 meters per second, and in our case, the wind is 4.5 meters per second, so it's still not
How
critical.
do you come up with this is the maximum wind that it will be subject to?
So it's the wind in the area of Spain. We have the maps, and this is the maximum area of the maximum wind in the whole area.
You got
The maximum recorded wind
Yeah, we
Yes,
have the
is
maps.
only 10 miles per hour?
Yes.
Yes, the whole area.
Yeah, we got wind maps of Spain, and in that area, the speed was 4.5 meters per second at that height.
Is that ever measured to 10 miles?
No, we have been
You had a wind map on a certain day?
يعني we got it for one of the boats, we don't know if that's a maximum.
We actually, it's has a return period, plus a short return period. It's taken.
So what if the bridge is subject to higher wind?
It's not considered because as we're relying just on the maps, but even if
What I'm saying is that the map represents an average case or a worst case, or worst with a certain probability. You never.
we consider that the map is mentioning the
17
maximum.
kilometers per hour. This is not a wind.
That's the point, because below 5 meters per
I mean,
second.
so you went into a very sophisticated analysis using wind that will never subject the structure to something critical, right? How did you include your results into the structural design?
The angle of the inclination of the deck to the horizontal, because we wanted to have the optimum aerodynamic shape.
You must understand from the schematic that you showed us, you had vertical sides of the ducts. You were not inclined.
The outer words were inclined. The outer
outer ones were inclined.
The ones you showed were
They
inclined.
were in beams.
The vents are vertical.
Yes, this one.
The green are.
Oh, I see. I see. Was there any wind direction that would produce lift in the upward rather than in the downward?
No, we considered one direction.
I mean, is it more critical and unsafe for the bridge to have a force that would lift the deck or to push the deck down? Which one? Which one do you think is?
pushes up, that's more critical.
So, but she came up with actually
So
the
we want to
will push it down.
maximize the downward to fix it in the downward direction. Because we are
Well, I
afraid
mean,
of the upward direction.
May I ask you, when you say you want to, what are you going to do with the wind so that really it works in your favor?
So we will play with the angle of the
Yeah,
inclination.
but who controls the angle of the wind? You
The
control the
angle
angle
of
of the
attack,
wind?
you mean what angle?
This is the angle, but which way the wind is blowing? You put a horizontal wind?
Is the bird, I mean, other horizontal.
Yes.
It's only one direction.
Horizontal wind, and we optimized the shape so that we can get a down drag force rather than an uplift force. So we ran the different angles, and the angle we chose, which is 55 degrees, is the one that gave us the most down drag force that stabilizes the bridge and is causing any
My
aerodynamic.
last question is, how high the deck from the water surface? Did you take that into consideration?
Yes.
I thought you said that you tried to do the simulation as if this is put in a wind tunnel.
Yes.
So then,
No, I thought you
What
asked
is
this
the-
question is related because we talked about the height of the bridge from the river in another calculation.
what is the relation between a wind tunnel and using the fluid?
It's just a study to make sure because we
You
couldn't
mean
make
you have the results of the wind tunnel?
sorry?
I mean, why are you referring to a wind tunnel?
Because it's for the software it's complicated, our shape is complicated and it couldn't be done only this way. I refer to Dr. Lamia and the only way to do this is to set the boundary conditions. We couldn't do without certain boundary conditions because the software is not accepting rather than boundaries. You have to define your boundary. If I couldn't open to the if I should discuss boundaries.
question at the angle of inclination and dimension. Why did it start with 55 degrees? Because the curve shows the first one is 55 degrees.
Dr. 55 is for the aerodynamics.
Yes,
Yeah, we did.
why did you start with this 55 degrees?
Yeah, we didn't start with the 55 degrees. احنا actually draw the geometry of the cross section. يعني we determine the depth of the cross section and everything, and I have the actual dimensions, and then I take the incremental يعني 3 meters increase and decrease 3 meters.
You can go up to the graph that shows the conclusions. This is this one. You can see you have angle in degrees starting 55, 63, 1 point.
I have the actual cross section dimension. Then I added a few meters in this direction and subtracted few meters from this direction and have the angles. It's a random process. I started from a starting point and then
What I want to say here is you selected 55 as the most critical one.
it's not the most critical one. It produced the maximum downward first, which was our objective. We want to maximize the downward.
Are you sure that if you have another angle less than 55 it will not cause
Actually, we have to.
a higher value? Because it's the end of the curve. You don't know what will be the trend after this point. It can be increasing, decreasing.
It's actually a slope increase, not that big, small spots, and then it starts to decrease. However, if it was at a steep angle, like 100 degrees, probably it would be a good idea to.
So yeah, it starts starting with the trend.
And then we have to limit ourselves because it will be open and it will put all the angles.
Okay, may I see now what's the span of the bridge?
100 meters.
100 meters. And what was the deflection caused by the wind?
We did not apply any wind load on our model yet. We were just running the wind load on the live load so that we can optimize the cable forces.
Well, the magnitude of the uplift force, this is downward force or
Downward.
so it is 35 Newton.
Yes, because the wind speed is very small. So actually, accordingly, it will produce a small downward.
Yeah, this number in
So
comparison to
Because
live.
it's in relation.
35 Newton is
Because we're doing a 2D
you are applying
analysis.
3.5 kilogram.
Yes.
They are applying 3.5 kilogram per unit length of the bridge.
Yes.
Yeah, it's not
Applied on the
very
entire cross section.
It's a 2D analysis, and we're not considering all the dimensions of the bridge. We're only taking just a 2D, and it's not the
Yes.
whole.
In your 2D analysis, you took all of the cross section of the bridge. All of this cross section is only applied
Must be considered.
or is only subjected to 3.5 kilogram.
it's small. يعني حتى I said مش ضغط لامية عشان مش automatic. The force is small, but it's okay عشان in relation to the wind speed we have. The wind speed is very small. يعني after I told her the wind speed, she told me first it's when you're doing all this, the wind speed is very small, and below 5 meters per second we're not concerned with the effect of the wind.
And actually,
The number الحقيقة is so less.
هي she actually put the number عشان أكيد in relation with the wind speed it's okay. For this wind speed it's okay.
You should consider your design higher wind because this
But
might
actually
not be the work.
we're abided by the map now. The map
This is the
of
possible.
yeah, we got it from one of the we were looking for
National approach.
we got it from the
International code, yes.
استحالة.
Like,
Any international code is more stringent than what we have.
actually, the actual specifies a very high wind speed, but this, when we found, because it specifies a default speed. But we were told that if we had a specific wind speed for this region, we should use it.
Well,
Instead of using the default.
I would advise you that you should consider normal wind loads, neglect the 10 miles per hour because this is really unrealistic. I mean, you should consider something normal. Otherwise, I mean, the load 3.5 kilogram applied on the whole cross section it means that it is negligible. All of this work, I mean, it's not really effective because you are talking about very small numbers.
Because actually when I increase the wind speed as a client, like I got a bit bigger load, بس يعني بس abided by the speed I have.
Now you have to think of larger wind speed because these numbers are not really. The other thing is about your model. You selected to use the village. Are you representing the? May I see the model, please? So I believe that the horizontal lines, these are representing portion of the longitudinal section,
Yes.
which is I-shaped section like this.
Yes.
Right. How do they connect together?
We are connected, and there are fine lines that maybe the projector are not is not showing them.
There is a transverse members mesh.
How can you how do you get the cross section of this transverse member?
This Excel sheet got different equations for calculating. This is looking here at transverse frames, and this calculates the different section and properties of each of them.
But I have a concern here that for the longitudinal member, we are including the top slab and the bottom slab as well as the web. You are taking it as I-shaped section. And then you are taking also the transverse frame, so you are duplicating the material.
That's why we mentioned that our weight modifier, which is how much the weight will be accounted for in the transverse member, is equal to 0. That's why, as if it's weightless.
So we use the stiffness in both directions, however we use the weight in one direction.
So your model will be 100% correct to model the loads, but it wouldn't be effective in modeling the plate action because you divided the system rather than having a single plate stiffened with webs. It will be just a grid of these.
This one outside of the village, that the transverse distribution of the load is not that accurate, so it needs more refinement.
So when it comes to the design of the slabs, we may need to
have to
of course, and we have to apply the other loads like the tandem load in Ashton because that magnifies the moment in the transverse direction. Yeah. So
what is the purpose of this village model?
So the global longitudinal behavior. Yes, the global and basically the longitudinal.
How do they connect these grids or these longitudinal beams? How do they connect to the final?
We have one web, as you can see, two webs and one pylon, and the pylon is big enough to cover up to these two places. So we have
representing also the pylon with the frame.
With a frame, and that frame is connected with two link members so that they transfer the moment, because we have a moment connection between the two webs or the deck link and the pylon. So we use these two links so the moment is transferred between the two webs. Because when we firstly we fix it the pylon at this moment, all of the moment of the pylon was not transferred to the deck, and this increased the moment of the foundation. So we have to do that, and this optimized the design actually.
Do you have a rigid link with the pylon like this? And the cables are in the same plane of the pylon?
No. Yes.
They are in the same plane. So how do they connect to the deck afterwards? Because the cables will be in between these two longitudinal beams.
No, we have two cables. We have pairs of cables, as you can see here. So these two cables fall at the same location of the two webs. So we use these link members to connect them to the pylon. However, each cable is connected to a web.
What is the pylon?
That's the pylon, and that's a cable, and that's another cable. And
okay, so this the cable left and right of the pylon, and still it's connected to the rigid link.
Yes.
And as for the connection between the cables and the deck, they are connected
to the website.
To the website.
To the website, yes, because they are on the In the real size, the pilot takes the space between these two wells.
Yes.
Did you get any results regarding deflection forces?
Yes, we got regarding the deflection, we have we did not optimize the forces in the cables completely. However,
This is due to the tightness of the cables.
yes, so at an average of 10 meganewton in each cable, we have a 6 centimeters positive deflection. At 8 meganewton deflection, at 8 meganewton force in each cable, we have around 14, maximum of negative 14 centimeters deflection.
But you applied also the red load.
These are the deflections for the dead load. I did not include deflections for the live load so that I can make a good comparison, because the live load deflection varies according to the tightness of the cables too. So it will not be fair to make a clear judgment about the cable forces as a start in our stage right now.
I know I haven't looked at the question, but I'd like to call your attention to the slides not followed, and you should rehearse that before you finish your presentation. Try to first in an environment similar to that, so it will be clear that these people will be able to see what you're trying to say.
I'll try to be as short as possible. I start by a question which just took me from the session. You have numerical model, right? How do you know that those results are correct?
We compare them to other cable stayed bridges. We compare the areas of the cables. The depth is actually to determine the 3-meter depth of the box section. We did a literature review over around 7 bridges, and we calculated the span to depth ratio of all of these cable stayed bridges, and we accounted for either they have 1 pylon or 2 pylons, and we came with these numbers, and they were close to the ones used.
This is your answer, right? So have you heard about something called schematic or preliminary design, something like that? Have you heard about checking using hand calculations, single hand calculations?
Actually, we didn't, because the system was completely complex. We actually tried to calculate the cable forces by hand, but we had to solve like the 13 by 13 matrix to find the initial cable forces or the starting cable forces. So we skipped into the numerical analysis, and we kept checking on our results with other cable bridges that are existing, and we checked also with our advisor and he confirmed.
My second question, can we do linear analysis on those cables?
No.
Why?
Because we sag, there is non-linear geometric non-linearity, but the linear analysis with cables is like, it does not make sense.
Not there. Yes. When the first time it will sag, the forces, the tension forces along the cable will not be along the straight line, and the deflection will not make it.
Let me rephrase my question. How do you generate the force in the cable?
We use the frame elements, and
how do these forces are generated in the cable?
they are pre-tension, they are jacked.
So in order to generate force, you have to have a deflection, right?
Yes.
And the force depends on the deflection.
Yes.
So my question stands, can you do a linear analysis?
Yes. A linear, no.
What kind of tools are you going to use in design? I've noticed that you have truck loads from Ashton.
Yes,
We're using the roots from the Ashton. I'm using the design codes of the ACR.
Of the
ACR SI 380.
Runtime. You mentioned that you didn't use, you are always using reduced model. Okay? And I wanted to know the runtime for the reduced model. How long does it take?
For the dead load only, it takes like 3 minutes. However, for the dead load and the moving loads, it takes like, yes,
10 minutes, half an hour.
yes, like
But
25
for the area elements,
So your computational requirement is the maximum with the non-linear and full loading and blah 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 in half an hour
with grillage.
with grading.
that's why we substitute
That's
the
not
area.
not use a full model. 3D analysis is area or solid elements and this.
The area allotted.
So if you are telling me that your model is taking half an hour, so your full model may take 1 day. If we have a computer which can run Revit model, most probably your model will take 1 hour.
Revit model technical.
Yeah, something else. But you're on a computer that can do it to your model, your full 3D model will take 1 hour to 2 hours at most. So there is no excuse of using a reduced model as opposed to full model, and you avoid all this kind of stiffness on the other direction like that.
Regarding 3D model, what do you mean by 3D model? You mean area elements?
Shell elements, solid elements, if you need, cable elements, everything.
Well, we use cable elements and frame elements for the pylon, and that's fine. For the deck,
For
we
the
use
deck?
the grillage instead of the
My
entire
question,
area.
why don't we
The
use
problem
the
with area elements that they magnify the negative moment and they underestimate the positive moment. That's why we had to get out of that loop. And actually, at the end, we are gonna run one area element model to verify our findings.
So using the area model is not correct in the first place.
It's about efficiency.
Yes.
It's about efficiency.
In efficiency and saving time.
Time saving time for the.
But this is the first argument. That your time will not exceed 1 or 2 hours.
Our lab computers does not have this computation power.
Okay, so it's no.
If we have a computer like this,
I think you will have one because I asked it and I found that we have a computer which runs VRM models. So if our computers run Revit,
that's for the.
SAP, and all these numerical models are nothing. So we can compare it for 1 hour. Anyway, these are the questions which I know the answer to. The other question I have to comment you in work because I myself cannot do it. And I tell you the level of professionalism you reached. We are talking about computational fluid mechanics. I need to elaborate on that. What's computational fluid mechanics? What do you do?
Computational fluid dynamics, it's
Computational fluid mechanics. Computational fluid dynamics. Okay.
it's the science of solving the dynamic equation in using the several equations.
Choose the software.
Okay, be careful with computational fluid mechanics or dynamics, whatever, because my experience with that, we run it on a real project. I'll give you an example, the clock, the CFRB clock in Mecca. We have a wind tunnel, okay, and we did the analysis, and we did the design review, and after we finished everything, and while we are building this clock, the CFM or CFD give us double the value of the wind. Double the value of the wind. Double the value. And that was using ANSYS. So be careful with that. Results, and try to check it once.
Maybe I answered this question was through the validation that came from discussing with the student.
You didn't validate your numerical model on SAP, so how did you validate your validation mechanics model?
By using running the model around the cylinder, and the answer is no. So actually,
So you validate that
yeah,
model?
the same value is entered here and here, and we have
You will be the one to validate CFD.
no validate CFD.
CFD is commercial. So I would rather see that you really apply it on the practical case by holding the deck above the water by the right side. Instead of saying this, I cannot simulate the dock.
No, I didn't say I can't
CFD
simulate.
is commercial and it should already be checked and validated 100 times.
Yes, I know, but our scope was something more simple here. In context, and all the work is done with Dr. Lamia, and she